Hello everyone, welcome to today's class. The topic that we are going to see today is Modern Symmetric Key Ciphers Part 1. The traditional symmetric key ciphers that we have studied so far are character-oriented ciphers. With the advent of the computer, we need bit-oriented ciphers. This is because the information to be encrypted is not just text, it can also consist of numbers, graphics, audio, and video data. In addition, when text is treated at the bit level, each character is replaced by 8 or 16 bits, which means that the number of symbol becomes 8 or 16 times larger. Thus, mixing a large number of symbols increases security. Now, moving on to the modern block ciphers, a symmetric key modern block cipher encrypts an n-bit block of a plain text or decrypts an n-bit block of ciphertext. The encryption or decryption algorithm uses a k-bit key. So as you can see from this diagram that for our encryption and decryption purposes, we are using n-bit plain text and the key that we are using is of k-bit key. Now this encryption algorithm and this decryption algorithm must be inverses of each other, okay? And they must use the same secret key, which is k. So if the message has fewer than n bits, padding must be added to make it an n-bit block. If the message, on the other hand, has more than n bits, it should be divided into n-bit blocks and the appropriate padding must be added to the last block if necessary. So the common values for this n-bit are 64, 128, 256 or 512 bits. A modern block cipher can be designed to act as a substitution cipher or a transposition cipher. Now in substitution modern block cipher, the plain text and the ciphertext can have different number of ones and zeros. For example, a 64-bit plain text may consist of a block of 12 zeros and 52 ones, and it can be encrypted to a ciphertext of 34 zeros and 30 ones. But for transposition cipher, this is not the case. In transposition cipher, the bits are only reordered. That is, there is the same number of ones and zeros in the plain text and the ciphertext. So modern block ciphers are usually designed as a substitution cipher because the inherent characteristics of transposition cipher, which is basically preserving the number of ones and zeros, makes the cipher vulnerable to exhaustive search attacks. Now moving on to the components of modern block cipher. Modern block ciphers normally are keyed substitution ciphers in which the key allows only partial mappings from the possible inputs to the possible outputs. However, modern block ciphers are normally not designed as a single unit. To provide the required properties of a modern block cipher, which is the diffusion and confusion, a modern block cipher is made up of a combination of transposition units, substitution units, and some other units. So in transposition units, we will get to see P boxes, and in substitution unit, we will get to see S boxes. So the properties of modern block cipher that I have shown is the diffusion and confusion. So let us see what they are. The idea of diffusion is basically to hide the relationship between ciphertext and plain text. Diffusion implies that each symbol, character or bit in the ciphertext is dependent on some or all symbols in the plain text. So in other words, if a single symbol in the plain text is changed, several or all symbols in the ciphertext will also be changed. Now moving on to confusion. The idea of confusion is basically to hide the relationship between the ciphertext and the key. So in other words, if a single bit in the key is changed, most or all bits in the ciphertext will also be changed. So these are our two properties, diffusion and confusion, where diffusion is basically hiding the relationship between our ciphertext and plain text, and confusion is hiding the relationship between our ciphertext and key. Now moving on to the transposition unit, which are our P boxes. So a P box, permutation box, parallels the traditional transposition cipher for characters. It basically transposes the bits. So there are three types of P boxes in modern block ciphers. They are straight P boxes, expansion P boxes, and compression P boxes. A straight P box is a P box with n inputs and n outputs. A compression P box is a P box with n inputs and m outputs, where m is less than n. So an expansion P box is a P box with n inputs and m outputs, where m is greater than n. So as we can see in this diagram, for a straight P box, the number of inputs and the number of outputs are same, right? N is equals to 5 and n is equals to 5 for our input and output. But for compression P box, we are seeing that the number of inputs is greater than the number of outputs. As you can see here, we had 5 inputs here, right? But for our output, we are only having 3 outputs. And in our expansion B box, as the name suggests, the number of inputs is lower than the number of outputs. As you can see, we had previously 3 outputs, right? But in our expansion B box, lastly, we will be having 5 outputs. The mapping between this input and output of these boxes are predetermined. So all of these mappings, they are predetermined. Only straight P box is invertible, which means it can be in the encryption cipher and its inverse in the decryption cipher. So it is pretty obvious that a straight P box can be invertible, right? But for compression P box and expansion P box, we can see in compression P box, some inputs are lost. We cannot recover these inputs in our decryption phase. So that is why this is not invertible. Same for expansion box, we cannot determine which inputs we have used twice. As you can see here, we are using 1 twice here, right? On the same hand, we are also using 3 twice here. So since we cannot decrypt this in our decryption phase, its inverse is not possible, which is why this is non-invertible. Now moving on to the substitution unit, which is our S boxes. An S box, substitution box, can be thought of as a miniature substitution cipher. So however, an X box can either have the same or different number of inputs and outputs. In other words, the input to an X box could be an n-bit word and the output can be an m-bit word, where m and n are not necessarily the same. So in this example, you can see that if our input is 110, so this leftmost bit for this S box will be counted over here. So the leftmost bit is 1 and the rightmost bits are 1 and 0. So here for 1, we will be looking into this row. And for 1 and 0, we will be looking into the columns. So we have a 1 here, and for the column, we have a 1 and 0 here. So matching this 1, 1, 0, our ciphertext will be 1 and 1. So if our input was 110, our ciphertext would have been 1 and 1. Although an X box can be keyed or keyless, modern block ciphers normally use keyless X boxes, where the mapping from the inputs to the outputs is predetermined. So which is similar to our P boxes, right? The mapping is predetermined. Now, if we want to see if our n bit and m bits, okay, that we are using are same, then we can see at this example. Now let us see here, we have 3 bits as our input, and for our output we can also have 3 bits. Say for example, if our input was 1, 1 and 1, so for our leftmost bit we will be checking this one, and for our rightmost bit we will be checking our column. So we can see for 1, 1, 1 we are having a ciphertext of 1, 1, 0. So 110 is the ciphertext. Okay, so this table that we are using, it's inverse. Okay, so the inverse of this table can be used for decryption as well. So an X box may or may not be invertible. In an invertible S box, the number of input bits should be the same as the number of output bits. So as you can see here, the number of input bits and the number of output bits are not the same, right? So this is not invertible, not. But here we can see the number of input bits the same as our output bits. That is why this S box is invertible. Now moving on to the exclusive OR. An important component in most block cipher is the exclusive OR operation. It has 5 properties. The first property is associativity. So this property allows us to use more than one exclusive OR operator in any order. So associativity, using associativity, which allows that we can use more than one exclusive OR in any order, suggests that we can do this operation. Okay, so X, XOR of Y, XOR of Z, And if this is in bracket, then we can also use x XOR of y, then XOR of z. Now, for example, in our XOR operation, what basically is happening? Okay, say for example, we have two inputs. They are x and y. Okay, so let me erase this. So we have x and y. Okay, so for our x and y, if they are 0, 0, 0, 1, 1, 0, and 1, 1, then for our XOR operation, what we will be having, what will be our output? So in our output, if the inputs, both of them are of the same bit, then the value will be 0. Okay, and if they are different, then the value would be 1. So this is how the XOR operation is done. Okay, so let me erase this and let me begin. So the next property after associativity is commutativity. Now this property allows us to swap the input without affecting the output. So as you can see here, x XOR y can be written as y XOR x. So the result will be the same. After commutativity, we have the existence of identity. So this implies that the exclusive ORing of a word with the identity element, which is 0, 0, 0, does not change that word. If we perform an operation where x exclusive OR with the identity element, then we will be getting x. Okay, so this property is known as the existence of identity. So this is very important. We will be seeing this property used in other ciphers as well. Then we have the existence of inverse. Now this implies that the exclusive ORing of a word with itself yields the identity element. If we perform an operation where the x is exclusive ORed with itself, then we will be getting the identity element. Now the last property is the complement property. So if x bar is the complement of x, then the following two relations hold. So x XOR x bar will give us 1, 1, 1. Okay, because since different bits will give us 1, that is why the result is like this. And for this, if we exclusive OR with 1, 1, 1, we will be getting x bar. Okay. The inverse of an exclusive OR operation can make sense only if one of the inputs is fixed. That is the same in encryption and decryption. For example, if one of the inputs is the key, which normally is the same in the encryption and decryption, then an exclusive OR operation is self-invertible. So here you can see in our encryption and our decryption, we are using a XOR operation. And in this XOR operation, the key, that is k, is fixed. So if this k is fixed, then it means that if we do exclusive OR operation, then this exclusive OR operation will be self-invertible. So as you can see in this example, we have y, and we have gotten this y after performing the exclusive OR operation with k and x, right? Similarly, if we want to achieve x from this, we can do so by exclusive ORing this y with the key. So basically, if y is equals to x XOR of k, then x is equals to y XOR of k. So if this is the case, okay, then only in that time this XOR operation is self-invertible. Okay. Now moving on to the product ciphers. Now Shannon introduced the concept of a product cipher. A product cipher is a complex cipher combining substitution X box, transposition P box, and other components like the XOR that we have seen. So a product cipher was made to maintain two properties, that is the diffusion and confusion we have just discussed. This diffusion and confusion can be achieved using iterated product ciphers, where each iteration is a combination of S boxes, P boxes, and other components as well. So each iteration is referred to as a round. So as you can see in this diagram, each of the iteration, okay, they are used as a round. And in each of this round, we have a combination of our key mixture, which is our whitener, a group of S boxes, and a straight P box. So the block cipher uses a key schedule or key generator that creates different 8-bit keys for each round. So this key generator, as you are seeing, or what it does it is creating 8-bit keys for each round. Okay, and in an n round cipher, the plain text is encrypted n times to create the ciphertext. The ciphertext, on the other hand, is decrypted n times to create the plain text. So we refer to the text created at the intermediate levels between two rounds as the middle text. Okay. So this is just the introduction of our product cipher. Now let us dive deeper into how all of this functionalities combine and how are they used. So as you can see, for our plain text, we are taking a 8-bit plain text, right? So the 8-bit text is mixed with the key, which is also 8-bit, to whiten the text, that is hide the bits using the keys. So this is normally done by exclusive ORing the 8-bit word with the 8-bit key. Okay, so we are taking this 8-bit plain text and we are taking the 8-bit key that is produced from this generator, round key generator, and what we are doing, we are performing the exclusive OR operation. Okay, so after performing the exclusive OR operation, the outputs of the whitener are organized into 4 2-bit groups and are fed into 4 S boxes. So what is happening here, after we have done the exclusive OR operation, these the 8 bits are grouped into 2 bits, right? And they are fed into 4 of these X boxes. Okay, so 2 of the bits from each of the key mixture, okay, from this key mixture is fed into this S box. So there are 4 X box which will be taking 2 input bits from this key mixture, okay, each of the X box. So after this happens, the values of the bits are changed based on the structure of the S boxes in this transformation. So here the number of inputs and output of the Xbox are same. Okay, so the number of inputs that are going into this Xbox, the same number of outputs will be coming out of this Xbox as well. Okay, so 4 of this Xbox will produce 8 bits, right? A total of 8 bits. So afterwards, what happened? The outputs of the Xboxes are passed through a straight P box, which is this one, to permute the bits so that in the next round, each box receives different inputs. So in this way, there can be n rounds. Okay, so here we have shown only 2 rounds, round 1 and round 2. So in round 1, after the exclusive OR operation, the X box and the P box, okay, the text that we are getting is known as the middle text. And again, this middle text, what will happen is the same operation will be done over again. Okay, that is, it will go through a key mixture, then the X box, and then the P box. And as you can see, the keys are generated from this round key generator. So in this way, we can have n rounds and we can produce a 8-bit ciphertext in the end. So this is our product ciphers. Now, in our product ciphers, we are maintaining 2 properties, which is the diffusion and the confusion. So let us see an example how this is done. So as you can see in this plain text, okay, we can see that in the first round, the bit 8. So here we have the bit 8. After being exclusive OR with the corresponding bit of K1, which is this one, okay, this affects 2 bits, which are bits 7 and 8. Okay, and this is affected through this S box, right? Then what happens is bit 7 is permuted and it becomes 2, and then bit 8 is permuted and it becomes 4. So after the first round, bit 8 has affected bits 2 and 4. So now let us see what happens in the second round. So in the second round, this bit 2, after being exclusive OR with the corresponding bit of K2, it affects the bits 1 and 2, right? And this is affecting the bits 1 and 2 through this X box. This is the Xbox 1. Then this bit 1 is permuted and it becomes bit 6. Okay, and this bit 2 is permuted and it becomes bit 1. Similarly, for our bit 4, we can see that after it is going through the X box, it is affecting the bits 3 and 4. So after this 2 bits go through the P box, this 3 bit remains the same, okay, and this 4 and this bit 4, after going through the P box, it is affecting bit 7. So after the second round, bit 8 has affected bits 1, 3, 6 and 7. So as you can see that bit 8 has affected the bits 1, 3, 6 and 7 in our ciphertext. Okay, so going through these steps in the other direction from ciphertext to the plaintext shows us that each bit in the ciphertext is affected by several bits in this plaintext, which tells us that the relationship between the ciphertext and the plaintext is strong. So this is how the product cipher is maintaining diffusion, as the key of diffusion is to hide the relationship between plaintext and ciphertext. So changing this plaintext will affect the ciphertext over here 1, 3, 6 and 7. So that is how this diffusion property is maintained. Now let us see how this confusion property is maintained as well. So the confusion property can be achieved through using this product cipher, as we know. And how is it being achieved? So the 4 bits of the cipher text, that is the bits 1, 3, 6 and 7, okay, they are affected by 3 bits in the key. So bit 8, okay, that is in key, that is being exclusive OR with K1, okay, the key, and bits 2 and 4, which are being exclusive OR with the key K2. Okay, so going through these steps in the other direction shows us that each bit in each round key affects several bits in the ciphertext. So as a result, the keys K1 and K2, they are affecting the bits of the ciphertext. The bits are 1, 3, 6 and 7. So because of this, the confusion property is being maintained. Now, the key idea of confusion property is to hide the relationship between our keys and the ciphertext. Now, if any of the keys are changed, then these bits in the ciphertext will also be changed accordingly, right? So this is how the diffusion and confusion property in our product cipher is being maintained. Thank you. This will be all for today's class. Hope you have understood and enjoyed the class as well.